For, gosh, over 200 years, Newton's view of the universe, it was pretty much it, right? Absolute space, absolute time, like a clock ticking the same everywhere.
Yeah, it was the stage. Unchanging, rock solid. Until Einstein came along.
And bam. Suddenly, everything's relative. It wasn't just a little tweak. It was a complete paradigm shift. Really surprising, actually.
Well, what's interesting is that Newtonian physics worked great for, apples falling and planets moving mostly.
Well,
But by the late 1800s, people looking closely at light, at electromagnetism, they started seeing problems. Cracks in the foundation, you could say.
exactly. And that's what this deep dive is all about. We're going into Einstein's, his two huge ideas. Special relativity first, that deals with space, time, motion, when things are just cruising along, constant speed.
Right, no gravity in that one initially.
And then the big one, general relativity. His totally mind-bending theory where gravity isn't some mysterious force pulling things.
It's the shape of space-time itself. Curvature.
And these weren't just wild guesses, were they? These have been tested like crazy for a century. There's some really compelling evidence.
Absolutely. And, for you listening, it's important to get how science sees truth. It's not like some fixed rule book. It's about theories that work. Theories that describe what we see, predict new things accurately.
Consistently.
And Einstein's theories, they've done that incredibly well, better than anyone could have imagined, maybe.
So our mission today, we want to give you a really clear sense of these revolutionary ideas, look at the strong evidence that backs them up, and touch on why they're still so absolutely central to how we understand the cosmos. We'll be digging into scientific explanations, experimental results, some really cool stuff.
Yeah, should be fun.
Okay, let's jump in.
So before Einstein really shakes things up, let's appreciate what he was up against. That Newtonian world, absolute space, this kind of rigid grid, and absolute time, a universal river flowing the same for everyone, everywhere. That was physics for over 2 centuries.
Right, it feels intuitive, doesn't it? Comfortable. But then, late 19th century, things got weird, especially with Maxwell's work on electromagnetism.
Maxwell's equations, so elegant.
Yeah, and they predicted light was this electromagnetic wave traveling at a specific speed, see? But the equations didn't say what that speed was relative to. Relative to what?
Which naturally led people to ask, well, if light's a wave, what's it waving in? Like sound waves need air, ocean waves need water.
So they came up with the luminiferous ether, this invisible, undetectable substance filling all of space, the medium for light.
The idea was Earth must be moving through the stationary ether. Right, so there should be an ether wind, like sticking your head out of a moving car window.
And that brings us to the Michelson-Morley experiment in 1887. Really crucial. Their goal was precise. Measure the speed of light in different directions to detect this supposed ether wind caused by Earth's motion.
They built this incredibly sensitive interferometer, expecting to see a difference.
But they didn't. Nothing. A null result, they called it. No detectable difference in light speed, no matter which way they pointed the machine.
And this was, well, a huge blow, a crisis, really, for classical physics. If you can't find the ether wind, maybe the ether isn't there.
Which throws the whole idea of absolute space, the backdrop for the ether, into serious doubt.
Exactly. So Einstein's genius wasn't trying to somehow fix the ether model or tweak Newton.
No, he took a step back, a huge step back.
He said, let's re-examine the most fundamental things. Space and time themselves.
Yeah.
What if they are the things that need rethinking?
A totally radical approach. Instead of trying to make light fit the old rules.
He made the constant speed of light one of the new rules, a foundational principle. So in 1905, he publishes his paper on the electrodynamics of moving bodies. That's special relativity. Deals with constant motion, ignores gravity for the moment.
And then he spent another decade wrestling with gravity.
Right, leading to general relativity around 1915, 1916. That's where acceleration comes in. And gravity becomes this dynamic curvature of space-time.
And it's so important to stress that these weren't just philosophical musings. In science, theories have to match reality. They have to explain observations, make testable predictions.
They need coherence with evidence, unifying power. And Einstein's theories, as we're about to see, have just passed test after test with flying colors.
Okay, so let's dive into special relativity first. Where did it come from, fundamentally?
It really came from that clash we mentioned. Classical mechanics, Newton's laws, and Maxwell's electromagnetism just didn't quite mesh, especially about light speed. Einstein saw that you needed a new framework for space and time to make them work together.
And this new framework is built on just two basic ideas, two postulates. But they have massive consequences. Let's lay them out.
Okay, first postulate, the principle of relativity. Basically, the laws of physics are the same for everyone who isn't accelerating. So if you're in a smoothly moving train or standing still, the rules of physics work exactly the same way. Galileo kind of had this for mechanics.
But Einstein said, no, this applies to everything. All laws of physics. Electromagnetism, too.
Exactly. Bold extension. So your state of constant motion doesn't change the fundamental physics you experience.
Okay, that feels mostly okay. Bit abstract, maybe, but okay. The second one, though, that's the real kicker, isn't it? The speed of light thing.
That's the one. The principle of the constancy of the speed of light. It says the speed of light in a vacuum, c, which is incredibly fast, about 300 million meters per second.
Like 186,000 miles per second.
Right. That speed is the same for all observers in inertial frames, no matter how fast the light source is moving or how fast the observer is moving.
Which is just weird. Totally counterintuitive. Normally, if I throw a ball forward on a moving train, someone on the ground sees the ball's speed as the train speed plus my throwing speed.
Right. Velocities add up. But light doesn't do that. Whether you measure light from a speeding spaceship coming towards you or one moving away or one sitting still, you always measure its speed as c.
Always see. It's like a cosmic speed limit that's absolute for everyone.
Wow. Okay, so accepting that must really mess with our ideas of space and time. It forces you to abandon Newton's absolute space and absolute time. They can't be separate anymore. They have to be woven together into this single thing, four-dimensional space-time.
Space-time. Yeah.
And the rules for how measurements of distance and time change when you move from one frame of reference to another. Those are given by something called the Lorentz transformations. You can even think of them mathematically as rotations in this 4D space-time.
Rotations in space-time. Okay, my head's starting to spin a bit already. So what are the, tangible consequences of this unified space-time and constant light speed? What does it mean in practice?
Well, one of the weirdest is the relativity of simultaneity. Events that happen at the same time for me might not happen at the same time for you if you're moving relative to me.
Wait, what? Now isn't the same for everyone?
Nope. Imagine lightning strikes the front and back of a moving train exactly simultaneously according to someone standing on the platform beside the track. Someone sitting right in the middle of that train, because they're moving towards the light flash from the front and away from the flash from the back. They'll actually see the front flash first.
Yeah.
For them, the events weren't simultaneous.
Huh. So my now and your now could be different. That's unsettling. What else?
Yeah, you get time dilation. This is probably the most famous one after EMC2. Moving clocks run slower relative to stationary clocks.
Slower, like they actually tick slower.
Relative to the observer watching them move, yes. And it's reciprocal if we're moving relative to each other. I see your clock running slow and you see my clock running slow. The amount of slowing depends on the relative speed, governed by this Lorentz factor, gamma. The formula is basically delta 2pt equals. Delta t is the proper time, the time measured by a clock that's right there with the events.
So the faster you go, the slower time passes for you compared to someone standing still. That sounds like something out of a movie. Is there actual proof, like real-world proof?
Oh, absolutely. Loads of it. Classic example, muons. These are unstable particles created when cosmic rays hit the upper atmosphere.
Yeah.
They have a ridiculously short lifespan, like microseconds.
Okay.
Based on their lifespan and the distance, they shouldn't have nearly enough time to reach the Earth's surface before decaying. But they do. Lots of them reach us. Why? Because they're traveling so fast, near light speed, their internal clocks are running much slower relative to us on Earth. Time dilation extends their effective lifespan from our perspective.
Wow. So we see them living longer because they're moving fast.
Exactly. And then there's the Hafil-Keating experiment from 1971. They flew super precise atomic clocks around the world on commercial jets, some eastward, some westward. And when they compared them to identical clocks left back on the ground, the time differences matched the predictions. From relativity, you had to account for both special relativity due to speed and general relativity due to gravity differences, but it worked perfectly.
Incredible. And you can even measure this at slower speeds now.
Yeah, modern optical atomic clocks are so mind-bogglingly precise, they can detect the time dilation caused by just moving a clock up or down by less than a meter, or differences due to speeds of just a few meters per second. It's real.
Okay, I'm starting to believe it. Moving clocks run slow. What about distances? Does anything happen to space?
Yep, there's length contraction. A moving object is measured to be shorter in the direction it's moving compared to its length when it's at rest. Its proper length. The formula is $1 equals level gamma.
Shorter. So if I flew past you really fast, you'd measure my spaceship as being squished.
Only in the direction you're moving. Your ship's height and width would look normal to me, but its length would appear contracted.
Huh. Do we see this?
Well, again, it's only noticeable at really high speeds. Think about the Voyager space probe, moving pretty fast by our standards, around 17 kilometers per second. Its length is about 4 meters. The length contraction, less than 7 nanometers. Totally insignificant.
Ah, okay, so that's why we don't see things shrinking as they drive past. The speeds are just way too low compared to light speed.
Exactly. Newtonian physics is an excellent approximation for our everyday low-speed world because these relativistic effects, time dilation, length contraction, are always present, but they're just vanishingly small until you get up to significant fractions of c.
Right. It makes sense why it seems so strange to us. Okay, so time stretches, length shrinks. But there's one more huge piece from special relativity, the famous one.
Ah, yes. EMC2 dals.
Energy equals mass times the speed of light squared. Probably the most famous equation in the world. What's the deep meaning there?
It means mass and energy are, well, they're basically two sides of the same coin. They are equivalent, interchangeable. And that conversion factor, to $2 to the speed of light squared, is enormous, about 9, followed by 16 zeros in standard units.
So a tiny, tiny amount of mass is equivalent to a gigantic amount of energy.
Precisely. And this isn't just theoretical. It's the fundamental principle behind nuclear power. In nuclear fission, splitting heavy atoms, the pieces weigh slightly less than the original atom. That missing mass is converted into energy, according to EMC2 dollars.
Like in power plants or bombs.
Yep. And nuclear fusion, like what happens in the sun, fusing light atoms like hydrogen into helium. The helium nucleus also weighs slightly less than the hydrogen atoms that formed it. That mass difference is released as the tremendous energy that powers the sun and stars.
So the sun is constantly converting mass into energy.
Millions of tons per second, actually.
Yeah.
It also implies that even an object at rest has an inherent energy, its rest energy, just by virtue of having mass. And it's crucial in particle physics, too. Energy can create particles with mass, and particles can annihilate each other, converting their mass back into pure energy.
And does mass change with speed, too?
Yeah, the theory shows that an object's relativistic mass increases as its velocity increases. Is quite a cuzzer, gamma m dollars. Again, it's negligible normally, but becomes significant near light speed. It's part of why you can't accelerate a massive object to the speed of light. The energy required will become infinite.
Oh, so special relativity gave us this completely new picture of space, time, mass, and energy, especially at high speeds. But it left out gravity.
Right, that was the next mountain to climb.
So how did Einstein bring gravity into this new relativistic world? That led to general relativity, right?
Exactly. Special relativity was 1905. But Einstein knew it was incomplete because it didn't include gravity, and it only dealt with constant velocity, not acceleration. He spent the next 10 years working on it, at a real intellectual struggle.
I bet.
And the breakthrough, the key insight, was the equivalence principle.
The equivalence principle. Okay, what's that about?
It's a deceptively simple but profound idea. It says that locally, like in a small region of space-time, you cannot tell the difference between being in a gravitational field and being in an accelerating frame of reference.
Okay, unpack that a bit.
Einstein used the thought experiment. Imagine you're in a closed box, like an elevator, with no windows. If the box is sitting on Earth, you feel your weight pulling you down due to gravity.
Right, normal gravity.
Now imagine the box is out in deep space, far from any gravity. But a rocket attached to the top starts accelerating the box upwards at exactly 9.8 meters per second, squared the same acceleration as Earth's gravity. Inside the box, you'd feel a force pushing you against the floor, exactly like you feel weight on Earth. Your feet would press down. If you dropped a ball, it would fall to the floor. From inside the box, you'd have no experiment you could do to tell if you were sitting still on Earth or accelerating in space.
Huh. So gravity and acceleration, they feel the same. Locally?
No, locally, yes. Indistinguishable. This was the bridge Einstein needed. If acceleration affects space and time measurements, which follows from linking special relativity to accelerating frames, and acceleration is equivalent to gravity, then gravity must also affect space and time.
Ah, okay. So gravity isn't just a force acting in space-time. It's connected to space-time.
Precisely. And it led to this radical conclusion. What we perceive as the force of gravity is actually a result of objects moving in curved space-time. Free fall, like an astronaut floating in orbit, isn't being pulled by a force that's somehow balanced out. It's actually inertial motion following the straightest possible path, called a geodesic, through space-time that has been curved by mass and energy.
So like rolling a marble on a stretched rubber sheet with a bowling ball in the middle. The marble follows the curve.
That's the classic analogy. The bowling ball, like the sun, warps the rubber sheet, space-time, and the marble, like a planet, follows the curve created by the bowling ball. It looks like the ball is attracting the marble, but the marble is just following the geometry of the curved surface.
So gravity is geometry. Mass and energy tell space-time how to curve.
Exactly. The more mass or energy you have packed into a region, the more space-time curves around it. And it's dynamic. If the mass moves, the curvature changes and ripples outward, which, as we'll see, is the origin of gravitational waves.
And this whole complex relationship, mass curving space-time, curved space-time guiding mass, that's all encoded in Einstein's field equations. They look terrifyingly complex.
They are mathematically complex, yes. 10 coupled, nonlinear partial differential equations.
Yeah.
But the core idea, conceptually, is what we just said. One side of the equation, involving the Einstein tensor and the metric tensor, describes the geometry of spacetime, how it's curved.
Okay. Geometry side.
The other side, with the stress energy tensor, describes the distribution of mass, energy, momentum, pressure, all the stuff in spacetime that causes the curvature. And they're linked by constants, like Newton's gravitational constant g and the speed of light c. There's also the cosmological constant lambda, which Einstein initially added to get a static universe, later called it his biggest blunder, but now it's back, linked to dark energy.
So the equations basically connect the stuff to the shape.
Perfectly put. John Archibald Wheeler had that famous summary. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. That's the essence of general relativity.
And it's built on fundamental principles we observe, like all objects falling at the same rate in gravity.
Exactly. It's a principle theory, derived from these very general, empirically discovered characteristics of nature, not from hypothesizing specific mechanisms like, say, tiny particles carrying the gravitational force.
Okay, mind officially bent. Special relativity changed space and time. General relativity turned gravity into curved space-time geometry. Incredible ideas, but science needs proof, right? How do we know this isn't just some incredibly elegant mathematical fantasy?
Absolutely crucial question. And the amazing thing is, over the past century, both theories have been subjected to incredibly rigorous experimental and observational tests. And they've passed with flying colors again and again.
So let's talk evidence. Starting with special relativity, we mentioned muons and atomic clocks for time dilation. What else?
Well, the Michelson-Morley experiment, even though it came before SR, its null result was powerful support for the constancy of light speed, which is postulate number 2. It really did shake things up back then.
Right, and particle accelerators, they rely on SR.
Completely. Particles and accelerators, like the LHC at CERN, are pushed to speeds incredibly close to c. Time dilation is massive. Unstable particles survive much longer than they would at rest. Relativistic mass increase is huge. The calculations needed to design and operate these machines are entirely based on special relativity. Without it, they just wouldn't work.
Okay. And length contraction. You said it's hard to see directly.
Very hard. But there's indirect evidence. For example, in collisions of heavy ions moving near light speed, they appear flattened due to length contraction, leading to higher densities than you'd otherwise expect. Also, the electric field of a fast-moving charge gets kind of squashed or intensified in directions perpendicular to motion, which is related.
In EMC2, that's tested every day in nuclear reactors and explains how stars shine.
Precisely. Nuclear fission and fusion are direct, large-scale demonstrations of mass converting into energy exactly as the equation predicts. We wouldn't have nuclear power or understand stellar evolution without it.
What about other tests, like really checking that light speed is constant?
Yeah, numerous experiments beyond Michelson-Morley have confirmed c is constant, regardless of the source's speed. Observations of light from distant binary stars or gamma-ray bursts show the light all arrives at the same time, regardless of the star's motion towards or away from us, or the light's energy. If light speed depended on source speed, we'd see weird smearing effects that we just don't observe.
And things like the Doppler effect.
Relativistic Doppler effect measurements, starting with the Ives Stilwell experiment back in the 30s and 40s, and continuing with modern techniques, precisely match SR's predictions, including effects that classical physics doesn't account for. Even magnetism, fundamentally, can be understood as a relativistic consequence of electric fields from moving charges. Technologies like generators depend on these principles.
Okay, so the evidence for special relativity seems really solid, woven into physics and technology.
It's foundational at this point, tested to extraordinary precision.
Now, what about general relativity? That seems even wilder. Gravity as curved spacetime. How do you test that?
Well, GR made some very specific testable predictions right from the start, different from Newton's gravity. One of the first big triumphs was Mercury's orbit.
Ah, the perihelion precession.
Exactly. Astronomers had known for decades that Mercury's elliptical orbit wasn't quite stable. The point closest to the Sun, the perihelion, shifts slightly with each orbit. Newtonian gravity, even accounting for all the other planets, couldn't quite explain the full shift. There was a tiny discrepancy, about 43 arcseconds per century.
Tiny, but measurable and unexplained.
Right. And Einstein, in 1915, applied his new GR equations to Mercury's orbit, and bam! It predicted exactly that extra 43 arcseconds per century. It just fell out of the theory naturally from the way the sun curves spacetime near it. Modern radar measurements confirm this for Mercury, Venus, and even Earth.
That must have been a huge confidence booster for him.
Oh, absolutely. And then came the prediction that gravity should bend light.
The 1919 eclipse expedition, led by Eddington, that made Einstein famous overnight, right?
It really did. GR predicted that starlight passing close to the sun should be deflected by the sun's gravity by a specific amount, about 1.75 arcseconds. During a total solar eclipse, you can photograph stars near the sun's edge. Eddington's teams went to Brazil and Príncipe Island off Africa.
And they saw the shift.
Their measurements were noisy, but consistent with Einstein's prediction, and definitely inconsistent with the Newtonian prediction, which was 0 or half the amount, depending on assumptions. It was hailed as a major confirmation. Modern measurements using radio waves from distant quasars passing the sun get deflected exactly as GR predicts, now confirmed to about 0.03% precision using very long baseline interferometry.
Incredible precision. What else does GR predict? Effects on time.
Yes. 2 key effects. Gravitational redshift. Light climbing out of gravity well loses energy, shifting its frequency toward the red end of the spectrum. This was confirmed in a lab experiment by Pound and Rebke in 1959, measuring gamma rays going up just 22.5 meters in a tower at Harvard.
Wow, over that short a distance.
Yep. And it's observed astronomically, too, like in light from dense white dwarf stars like Sirius B.
Okay, redshift. What's the other time effect?
Gravitational time dilation.
Yeah.
Clocks run slower in stronger gravitational fields. Clocks closer to a massive object tick slower than clocks farther away.
Like time dilation and SR are due to speed, but this is due to gravity.
Exactly. This was also confirmed by flying atomic clocks at different altitudes. The Half-Felic-Keating experiment again, they had to account for both effects. And modern, ultra-precise atomic clocks can measure the difference in ticking rate between two clocks separated vertically by just tens of centimeters.
That's insane precision.
It is. And this effect isn't just academic, it's absolutely essential for the Global Positioning System, GPS, to work.
Really? How so?
The GPS satellites are orbiting high above Earth, where gravity is weaker, and they're also moving fast. Both special and general relativity affect the timing signals when they're onboard atomic clocks relative to clocks on the ground. GR predicts the satellite clocks run faster due to weaker gravity, about 45 microseconds per day faster. SR predicts they run slower due to their speed, about 7 microseconds per day slower.
So there's a net effect.
Yeah, a net effect of about 38 microseconds per day that the satellite clocks run faster than ground clocks. If the GPS system didn't constantly correct for this relativistic difference, your calculated position would drift off by about 10 kilometers every single day.
Whoa, so relativity isn't just theory, it's in my phone making the map work.
Pretty much. Then there are even more exotic effects, like frame dragging.
Frame dragging, sounds cool.
It's the idea that a massive rotating object, like the Earth, should literally drag space-time around with it as it spins, like stirring thick honey.
Okay, how do you test that?
It's a very subtle effect. The main experiment was NASA's Gravity Probe B mission. Launched in 2004, it used incredibly precise gyroscopes orbiting Earth over the poles. After years of painstaking data analysis, they announced in 2011 that they had measured the frame dragging effect, consistent with GR's prediction to about 19% accuracy. There's also evidence from laser-ranging satellites and observations of binary pulsars.
Binary pulsars, they seem important for testing GR.
Hugely important, especially systems where two pulsars orbit each other, or pulsar orbits another neutron star. These are incredibly dense objects in strong gravitational fields, moving very fast. They are perfect laboratories for GR.
What do they tell us?
Well, the first big discovery was the Hulse-Taylor binary pulsar in 1974. GR predicts that these orbiting massive objects should lose energy by radiating gravitational waves. This energy loss should cause the stars to spiral closer together and their orbital period to decrease over time.
And do they?
Precisely. Hulson-Taylor measured the orbital decay over decades, and it matched the prediction from GR's gravitational wave emission formula almost perfectly. It was stunning indirect evidence for gravitational waves and earned them the Nobel Prize in 1993. Other binary pulsars, like the double pulsar system, have confirmed GR's predictions in even more ways and to higher precision.
So that was indirect evidence for gravitational waves. But then we detected them directly.
Yes, that was the absolute game changer. LIGO, the Laser Interferometer Gravitational Wave Observatory, made the first direct detection on September 14, 2015, a signal named GW150914.
I remember the buzz around that. What did they see?
They detected the ripples in spacetime caused by two massive black holes, about 29 and 36 times the mass of the Sun, spiraling into each other and merging, about 1.3 billion light-years away. The waveform, the shape of the signal, matched exactly what GR predicted for such an event.
Wow, hearing the universe in a way.
Exactly. It opened a whole new era of gravitational wave astronomy. Since then, LIGO and the Virgo detector in Italy have detected dozens more events merging black holes, merging neutron stars. It's confirming GR in the most extreme gravitational environments imaginable.
And speaking of extreme environments, black holes themselves, GR predicts them, and now we're imaging them.
Yes, black holes are maybe the most extreme prediction of GR regions, where gravity is so strong, nothing, not even light, can escape. GR makes specific predictions about what the region just outside the event horizon should look like as shadows cast against the glowing background material.
And the Event Horizon Telescope, EHT.
Exactly. The EHT, this global network of radio telescopes acting like one Earth-sized dish, managed to capture the first image of the supermassive black hole at the center of the M87 galaxy in 2019, and later the one at the center of our own Milky Way, Sagittarius A.
And the images matched the predictions.
Remarkably well. The size and shape of the shadow are totally consistent with GR's predictions for black holes of those estimated masses. It's an incredible confirmation of the theory in the strong gravity regime right near the event horizon.
Okay, one more. Gravitational lensing.
Right. GR predicts that mass curves spacetime, and light follows those curves. So a massive object like a galaxy or a cluster of galaxies can act like a lens, bending and magnifying the light from objects located behind it.
And we see this happening
All the time. We see multiple images of the same distant quasar lensed by a foreground galaxy. We see distant background galaxies distorted into arcs and rings by massive galaxy clusters acting as lenses. It's become a vital tool in astronomy used to study distant galaxies, map the distribution of mass, including invisible dark matter, and even measure the expansion rate of the universe. The James Webb Space Telescope uses lensing frequently.
So the evidence just keeps piling up, from the solar system to black holes to the distant universe. It's really quite overwhelming.
It is. And the precision of these tests keeps improving, and GR keeps passing. Its truth, in the scientific sense of accurately describing and predicting nature, is incredibly well established within its domain.
So it's clear relativity isn't just some abstract theory. It's fundamentally reshaped how we even think about the cosmos.
Profoundly. General relativity isn't just about planets and stars. It's the framework for modern cosmology, the study of the universe as a whole.
How so?
Well, when you apply GR's equations to the entire universe, they predict a dynamic universe, one that must be either expanding or contracting. This led directly to the Big Bang model, the idea that the universe began in an incredibly hot, dense state and has been expanding and cooling ever since.
Even though Einstein himself initially resisted the expanding universe idea.
Yeah, he introduced that cosmological constant originally to try and keep the universe static because that was the prevailing belief. But the equations naturally pointed towards expansion, which was later confirmed by Hubble's observations of receding galaxies.
So the Big Bang model relies on GR.
Absolutely. GR underpins our understanding of cosmic expansion itself, the stretching of space-time carrying galaxies apart.
Yeah.
It's essential for Big Bang nucleosynthesis, explaining how the lightest elements like hydrogen, helium, and lithium were formed in the first few minutes, and it predicted the cosmic microwave background radiation.
The afterglow of the Big Bang.
Exactly. That faint radiation filling the universe, discovered in 1965, is perfectly explained as the leftover heat from the early, hot universe, cooled by expansion. Its properties, mapped with incredible precision, are a cornerstone of the Big Bang model and provide strong support for GR on cosmic scales.
And black holes, gravitational waves. GR is needed for all of that cosmic picture.
Yep. Understanding the end states of massive stars, the powerful engines driving quasars, the cataclysmic events detected by LIGO Virgo, even how the large-scale structure of the universe the cosmic web of galaxies and voids formed from tiny initial density fluctuations. GR is the essential tool. The fact that it works so well, extrapolating from local tests to the scale of the entire observable universe, is just remarkable.
And we already touched on the tech applications, like GTS. It's not just abstract science.
Not at all. We talked about GPS needing both SR and GR corrections to function. That's a daily practical application impacting billions of people.
And nuclear power and weapons based on EMC2.
Foundational. Even older tech, like those bulky CRT televisions and monitors, the electrons inside were accelerated to maybe 20–30% of light speed. Designers actually had to account for the relativistic increase in electron mass when designing the electromagnets that steered the beam.
No way, really?
Yep. Small effect, but necessary for sharp focus. And modern particle accelerators, as we said, are entirely reliant on SR principles for design and operation. Understanding magnetism as a relativistic effect of electricity underlies generators, motors, transformers, so much of our electrical world.
So relativity's truth isn't just theoretical, it's baked into our technology and daily lives.
It really demonstrates its validity in a very concrete way.
So what's the overall feeling in the scientific community now? Is relativity considered solved or complete?
The consensus is overwhelming. Both special and general relativity are seen as extraordinarily successful theories, robustly validated within their applicable domains. Special relativity is just considered a standard, indispensable part of physics, tested to phenomenal precision tests of Lorentz invariance, the core symmetry, are good to parts in 10 to the power of 20.
Wow. And general relativity?
General relativity has passed every single observational and experimental test thrown at it so far, from the weak gravity of the solar system to the incredibly strong gravity near black holes and in binary pulsar systems. As one review put it, GR successfully accounts for all data gathered to date. They are foundational frameworks.
But they've also had a huge philosophical impact, haven't they? Changing how we think about reality itself?
Absolutely. The shift away from Newton's absolute fixed stage to this relative, dynamic, interwoven space-time. That's a massive conceptual leap. It forces us to question our deepest intuitions about space and time.
Like the relativity of simultaneity, the idea that there's no universal now.
Exactly. That challenges fundamental assumptions and has led to all sorts of philosophical discussions about the nature of time. Does the past still exist? Does the future already exist? The block universe model, where all moments in time are equally real, is partly inspired by relativity's picture of space-time.
Which then leads to questions about free will versus determinism.
Indeed. If the future already exists in some sense in the block universe, what does that mean for our choices? These are deep philosophical waters relativity leads us into. Even Einstein's way of doing physics, emphasizing principles derived from experience, seeking mathematical simplicity and unity. His theoretical approach has influenced how philosophers think about scientific knowledge and methodology.
So it really goes beyond just physics equations. It challenges how we perceive reality.
It suggests reality is much weirder and more wonderful than our everyday intuition tells us. Its truth extends beyond just calculations.
It's truly incredible. One mind grappling with inconsistencies leads to this whole revolution. But even with all this success, relativity isn't the final story, is it? There are still edges, frontiers where things don't quite fit.
That's right. As incredibly successful as they are, we know relativity, particularly general relativity, can't be the complete, final description of gravity and space-time. There are situations, extreme conditions, where it breaks down or seems incompatible with our other hugely successful theory, quantum mechanics.
The big one, quantum gravity. Why is it so hard to unite GR and quantum mechanics? They both work so well on their own scales.
It's fundamentally because they describe reality in very different languages. GR describes gravity as the smooth, continuous curvature of space-time, a classical field theory. Quantum mechanics, on the other hand, describes the microscopic world in terms of discrete units, quanta, probabilities, wave-particle duality, and weird uncertainty principles. It usually assumes a fixed, flat space-time background to operate on, which contradicts GR's dynamic space-time.
So they clash conceptually.
Deeply. When you try to apply standard quantum field theory techniques to quantize gravity, treating it like the other forces, you run into mathematical nightmares, uncontrollable infinities that make the theory nonsensical. There are also profound conceptual problems, like the problem of time, how time is treated differently in the two frameworks.
And we need a theory that bridges this gap.
We absolutely do. We need a theory of quantum gravity to understand what happens at the very center of black holes, the singularity, and what happened at the very beginning of the universe, the Big Bang singularity. These are realms where gravity is incredibly strong and quantum effects must be important because the scales are so small. Our current theories just break down there.
Are there promising candidates for a quantum gravity theory?
There are several research programs. Two of the most prominent are string theory, or M theory.
Where particles are tiny vibrating strings?
Basically, yeah. It posits that the fundamental constituents of reality aren't point particles, but tiny vibrating strings or higher dimensional brains. It requires extra spatial dimensions and aims to unify all forces, including gravity, in one framework. It has mathematical elegance and might resolve singularities by smearing out interactions.
Oh, okay. And the other one?
Loop quantum gravity, or LQG. This takes a different approach. It tries to directly quantize space-time itself, applying quantum rules to geometry. It predicts that space and time aren't continuous at the smallest scales, the Planck scale, incredibly tiny, but have a discrete granular structure, like atoms of space-time.
Like pixels of reality.
Kind of. LQG focuses specifically on quantizing gravity, not necessarily unifying all forces. It offers potential ways to resolve singularities, maybe replacing the Big Bang with a big bounce.
But neither of these is confirmed.
No. Both are highly mathematical and abstract, and crucially, they lack direct experimental verification so far. Finding experimental evidence for quantum gravity is one of the biggest challenges in physics today. So the fact that GR breaks down here tells us the limits of its domain. It's not wrong, it's just incomplete at those extreme scales.
You mentioned singularities, black hole centers, the Big Bang. Why are they such a problem within GR itself?
Because within the framework of GR, a singularity is a point, or region, where the theory predicts physical quantities like density and space-time curvature become infinite.
Infinite? That sounds bad.
It's generally seen as unphysical. It signals a breakdown of the theory itself. GR predicts a point-like singularity at the center of a simple, non-rotating black hole, or a ring-like singularity in a rotating one. And cosmological models based on GR, extrapolated back in time, hit an initial singularity of infinite density and temperature at the Big Bang.
So the laws of physics, as described by GR, just stop working there.
Pretty much. Paths of particles, geodesics, can just end abruptly at a singularity. The theory can't predict what happens at or beyond it. It's mathematically ill-defined.
And the hope is that quantum gravity will fix this.
That's the prevailing expectation. Quantum effects, which GR ignores, should become dominant at the Planck scale, preventing the uncontrolled collapse to infinite density. They might smear out or fuzz out the singularity, replacing it with something more physically sensible, like the big bounce idea in some LQG scenarios.
Okay, so quantum gravity and singularities mark one frontier. What about the universe on the large scales? You mentioned dark matter and dark energy earlier. Are they signs of GR's limits too?
That's the other huge mystery, and it's deeply intertwined with GR. Observations of galaxy rotation, galaxy cluster dynamics, gravitational lensing, the cosmic microwave background, large-scale structure. They all tell us there's much more gravitational influence out there than we can account for with the visible matter, stars, gas, dust, using general relativity.
So something's missing, or GR is wrong on those scales.
That's the big question. The standard explanation is dark matter. Some kind of invisible non-luminous matter that interacts mainly through gravity. It would make up about 85% of all matter in the universe, about 27% of the total mass energy content. We have candidate particles like WIMPs or axions, but haven't directly detected them yet.
So dark matter is trying to save GR by adding new stuff.
Essentially, yes. It assumes GR is correct, but there's just more stuff out there than we can see. But the other possibility is that maybe GR itself needs to be modified on galactic or cosmic scales.
And then there's dark energy.
Right. Observations of distant supernovae in the late 1990s showed the expansion of the universe isn't slowing down, as you might expect due to gravity, but is actually accelerating.
Speeding up.
Within the framework of GR, the simplest explanation is some kind of mysterious energy permeating all of space, with negative pressure acting repulsively. We call it dark energy. It seems to make up about 68% of the total mass energy of the universe, the dominant component. It could be related to Einstein's cosmological constant, lambda, but we really don't know what it is fundamentally.
So again, is it a real thing within GR or a sign GR needs changing?
Exactly the same dilemma. There are modified gravity theories, like MOND, TEAS, FR, gravity, that try to explain galaxy rotation or cosmic acceleration by altering the laws of gravity on large scales without needing dark matter or dark energy.
Do they work?
They have some successes, but also face significant challenges in explaining the full range of cosmological observations, as well as the standard model, which is called lambda CDM, Lambda for dark energy cosmological constant, CDM for cold dark matter. Lambda CDM, which uses GR plus these dark components, still provides the best overall fit to the vast majority of data.
But it feels a bit unsatisfying because we don't know what 95% of the universe is.
That's precisely the tension. Lambda CDM works incredibly well phenomenologically, but it's theoretically unsatisfying because its main ingredients are unknown. Recent surveys, like DSI, are testing GR on cosmic scales with ever-increasing precision, and so far, it seems consistent. But the mystery of the dark sector is profound and might ultimately point towards new particle physics, modifications of gravity, or perhaps something even stranger, potentially linked to quantum gravity.
It's incredible. Even our best theories lead us to these deep, fundamental unknowns. Okay, so let's try to wrap this up. Einstein's theories, special and general relativity, they are just monumental achievements in human thought.
Absolutely. They completely revolutionized our understanding of space, time, matter, energy, and gravity. And as we've seen, they are supported by a century of rigorous testing and observation. Their predictive power within their domains is just astonishing.
Special relativity handling high speeds and the equivalence of mass and energy. General relativity revealing gravity as the geometry of curved spacetime, governing everything from planetary orbits to the evolution of the entire universe. Their truth really lies in that robust predictive success.
They are bedrock pillars of modern physics. But as we just discussed, they aren't the final word. The unanswered questions, the need for quantum gravity, the problem of singularities, the enigma of the dark universe show us their limitations and point towards the exciting frontiers where physics is heading next.
And it's important, like you said, that current research isn't about throwing Einstein away. It's about standing on his shoulders, building on that incredible legacy, seeking an even deeper, more comprehensive understanding. His impact wasn't just what we know, but how we approach physics, that blend of principle, mathematical consistency, and challenging intuition.
He truly taught us how to think about the universe in new ways.
So as you, our listener, reflect on all this, just think about it. Our understanding of something as basic as everyday as gravity has been completely transformed. What other seemingly solid truths about our universe might just be waiting for the next Einstein, the next revolution in thinking, to reveal a reality even stranger and more amazing than we currently imagine? Makes you wonder what's still out there.
Definitely food for thought.
And that's where we'll leave this deep dive for today. Thanks so much for joining us.